Okay. Good evening, everyone. Welcome to week 5 problem solving session for the course on selected topics in algorithms. Okay. And my name is Bhavya Rai. I am a PhD scholar from IIT Madras. So, like always, we are conducting these lectures, these problem solving sessions on every Tuesday, 6 p.m. Okay, 6 p.m. to 8 p.m. Okay, great. Having said that, let us begin. So, we are continuing the uh, concepts of randomization this time. Okay, and this time the topic of study is what is called Markov chains. So again, it's a very interesting object, and Markov chains talk about how we can get closer to randomness. Okay, that in essence it is that, but it is actually also a model. It is actually also a model that captures um it is also a model that captures probabilities for different systems. What I mean by that is, okay, so a Markov chain can be said to be, uh, okay, Markov chain is, it can be thought of an object, okay. There are two interpretations, but one simple way to visualize this is an object, okay, and the object has various states, okay, and each of these states can be thought of as say x not x1, a1, a2, a3, and so on, okay, and these states may be infinite, okay, and what we are thinking of is that now, um, from each state ai, okay, it is possible to move from state ai to a state aj. It is possible to move from a state ai to a state aj with some probability aij, okay. Now, uh, of course, does it mean that I can always move from any state I to another state j? It may not be possible, because for that case I could set the probability to 0, okay. And one way to always visualize Markov chains is through graphs, by making a directed graph interpretation, okay. And okay, what is an interpretation for a direct graph? Well, I label the state, say a1 and a2 and a3, okay, and a4, okay, and then I say that, okay, I can move to a2. We've already seen what weighted graphs are, right? We've seen flows and stuff. Now, so here's how we can represent them. From a1 to a2, I can move with a probability of 0.1, and I can move to, yeah, okay, a3 with a probability of 0.9. Okay, I can move to a4 with a probability of, okay, now I've, it's 0.1, 0.9, so sum should always be at least, at most 1, okay. So yeah, it cannot move to any other state. So similarly, from a2 to a3, I move with a probability of 0.2, and a2 to a4, I move with a probability of 0.8, okay. And uh, from, and what is left? Okay, a3 is left, and so on, but it could be infinite. Now, another way to see it is by a matrix. Okay, another way to see it is by a matrix. That is, I say a1, a2, these are the rows, a4, and then I label it with columns, a2, a3, a4. Okay, so a1 moves to itself with a probability of 0. Okay, the row is representing from where I'm moving, column is representing to where I'm moving. Okay, I can move to a state A2, okay, with a probability 0.1, right? This. Now I can move to A3 with a probability 0.9, and similarly A4 with a probability 0. And then I'll do the same for A2 also. A2 I can move to from A2 I can move to A3 with a probability of 0.2. I can move to A2 to A4 with a probability 0.8, and the rest will be zeros. And then I'll keep filling this. Now this is what is called a probability transition table. Sorry, transition probability table, because this each of these values shows the probability of transitioning from one state to another. Okay. Transition probability table. Okay. So this is what the transition probability table is, and as you can see, all these three definitions are equivalent to each other. This is just the weighted adjacency matrix of this graph, and it's just that this is more visual, and to work with mathematically, to perform some calculations, maybe this is easier to do. And this is just the same definition, but visualized in terms of a graph. So all these three definitions are equivalent. Okay. There is a more formal definition to it also, but I think you've seen the definition in lectures. It just says that there is a probability associated with each random variable. Now the random variable, okay. Now the formal way to see it is, okay, there is a state space, okay, which is just a set, which is sometimes denoted by omega, okay, or A or some. And there's a state space which says this is your set of states, okay, A1, A2, and so on till AN. Okay, and there are these random variables x1, x2, x3, and so on, xt. Okay, now what is each of these things? Well, each. So what is each xi is the state of the current state, I'll say, okay, is the current state, okay, current state of the Markov chain. Okay, I'll make it xt, okay, at time t. What is time? Time is the number of steps. Okay, so it's not always that, say, x1 is, say, a1, and x2 is, say, a2, and x3 is, say, a1 back again, and something like that. This may not always happen. Usually what happens is x1 is a1 with probability half, and say a2 with probability half. And in the, okay, so what does that mean? Okay, or let me be more specific. Let's take this particular example. Okay, let's take this particular example. I'll copy this. Okay, yeah, Kishore.
Yes, intuitively, this is the state space as the A1, A2, A3, and up to AN.
Right.
So which physically, if you wanted to intuitively represent that, those are the vertices of the graph.
Those are the vertices of the graph. Correct.
And what about the random variables? So it also consists of x1, x2, x3, x3. Then how can we represent these in intuitively?
Yeah. So now what I'm saying, yeah, that's something I'm going to demonstrate. For example, okay. Now what I'm going to do is I'm going to simulate this Markov chain. Okay. So what do? I consider a start state. Okay. Let's say A1 is my start state. I start from A1. Then I run it for one step. when I run it for one step, I can either move with probability 0.9 to A3, or I can move with probability 0.1 to A2. This represents a random system. Okay, it's not a uniform random system because all the probabilities are not equal, but it is a random system. Okay, where I'm moving from one state to another. Now, let's say I um, I do one step. Then in that particular one step, I can consider myself to be simultaneously at A2 and A3. But I'm more likely to be at A3. So I can say something like, in one step, with probability 0.9, I am at A3. And with probability 0.1, I am at A2. Okay. So now you can see that what is x1 a2 and then you can continue. So let's not stop there. Okay, let's not stop there. Let's continue. Now that was t equals 1, right, in one step. Now let's move to the second step, t equals 2. Now I'm at A2 or A3. Okay, now if I'm moving from A3, what is the probability? Let's say with probability exactly 1, it was defined as probability exactly 1, I move to A4. Okay, and from A2 it's already defined. Okay, so now at t equals 2, if I was at A3, then with probability 1 I will move at A4. And if I was at A2, because remember in t equals 1 I should be either at A2 or A3, I cannot be at any other state, okay, with some associated probability. If I was at A2 in t equals 1, at the next step t equals 2, with 0.2 probability I'll be at A3, and 0.8 probability I'll be at A4. Right, so far it's good, right, Kishore?
Right.
Now, but starting at A1, what is the probability? For example, starting at A1, what is the probability that at t equals 2, I land at A4? There are two possible paths. One possible path is I go in step T1, I move to A3, and step T2, t equals 2, I move to A4. This is one way to do it. The other way to do it is, in one step I move to A2, and the other step I move to A4. There are two ways to do it. Okay, and maybe if t equals 3, then I could move it this way also. But we are talking about two steps. So what is the total probability of moving from A1 to A4? So what is the total probability of moving from A1 to A4? Well, it is the probability. Okay, it is the probability. How do I choose the line? Okay, yeah. It is the probability. So probability of moving from A1 to A4 is equal to the probability that I move from A1 to A3. A1 to A3. Okay, it's denoted this way. Okay, which is 0.9 times from here to here. Okay, times the probability I move to A4, because I'm doing this first I move to A1 to A3 and then I move A3 to A4. A3 to A4. Okay, so I do times the probability that I move from 3 to 4, or I move to A2 first. So probability that I move from 1 to 2 times the probability that I move from 2 to 4. Okay, so that is nothing but 0.9 times 1 plus 0.1 times 0.8. Right? So it will give you some answer. I think 0.98. In two steps, landing to A4 has a probability of 0.98. Okay, this is another way of interpreting it. And what do these x1, x3s represent? They represent the possible states. Okay, remember x1, x2 are just not normal variables. Okay, they just don't store a single value. They can store several values with different associated probabilities because they are random variables. So x1 means for example, x0 at time 0, okay, I am at a1 because my start state is a1. Okay, I am is equal to a1 with probability full 1. Okay, now what is x1 means at time 1, one step of my run, I can move from a1 to a2 in with probability 0.1, a2 with probability 0.1, and I can move to a3 with probability 0.9. And similarly x2, I can move from so this is at second t equals 2, right? If t equals 2, I can move from if given that a1 is my start variable, I can move to a4 with probability okay, I can only move to a4 probably. Oh no, I can move to a3 also. So I can move to a4 with probability 0.1 times 0.9, and I can move to a3 with from a2, right? If we were starting from a2, 0.2 times 0.9, 0.1 times 0.2, so that is this path, or else I could take this path. Okay, 0.9 times 1, sorry, 0.9 times 1, or I can move from a2 to a3, so 0.1 times plus 0.2, 0.1 plus 0.2, and this value will exactly come to this whatever we computed here, 0.98. So now you get it what these random variables represent, right? They represent the possible states that we can stay at with their associated probabilities given at a time t. Kishore, is that clear?
Yeah, but see, for the x2, right? So as we discussed, we are just taking we are just considering the two-step routes.
We are just considering the two-step, right?
Okay, 3.
Two-step
0.
When we start at a1.
Yeah, starting at a1, two-step. That is a1, a2, a4, and then a1, a3, a4.
And their associated probabilities. Starting at a1, I can land at a4 through two routes.
Yeah.
Okay. One is taking this upper loop of 0.9, and then with probability 1, I move to a4, which is 0.9 times, which happens with probability 0.9 times 1. And then the other route, I add
for 3, right?
Yeah.
In x2, right? A3 with probability 0.1, 0.2, you said.
0.1 times, sorry, it's not, it's times 0.2.
But that we are not considering here, right? A3.
Wait, 0.1. The other way to do it is so do this, or okay. Sorry, I made a mistake. This is fine. The other route is actually okay. That's it. Right.
No, but A3.
This is one way to go. This is another way.
Yeah.
That's right. Correct. Yeah. Sorry. Now, if we talk about A3, then we can do
so
that.
Here A4 is so. So A3 also we are considering here.
A3 also we are considering, meaning in two steps I can move to A3.
Yeah, A4.
In two steps I move to A4.
When we start from A1 to reach A4, one route is A1, A3, A4. That is A4 in the first step. That is x2 is equal to A4 in case with probability 0.9 and 1.
Right.
It is 0.9 times 1.
0.9 times 1.
Yeah. So the otherwise the A3 we said, right? A3. In A3, see, instead our target is to reach A4, not A3, right?
Oh no, yeah. Sorry, if A4, I was giving an example of this, right? But what I'm saying is, oh, you mean this? Wait, is this this part correct. You have 1 to 3, 1 to 3 to 4, 1 to 2, 2 to 1 to 2, 2 to 4. Okay, that this also is there. Okay, so this is also there. Sorry, this root is also there. We need to add for it. Plus 0.1 times 0.8. Huh. It can.
So what about,
Yeah.
so what about the sum of all the probabilities? I mean, do we need to take that value also into consideration, that the sum of the probability across the different paths must result into the value 1?
Some of the probabilities will always add to 1 for any random variable.
But then that is not happening here. I mean, where
It is
is the
happening
sum
here.
of the
0.1 plus 0.9 is 1. This will come to 0.98 and this will come to 0.02, which when you add, it will become 1.
No, the first step one is very clear because it's single step. We are directly from A1 to A3 and A1 to A2. So that's very clear. But when we come to X2, right? So step 2, where T is equal to 2. So we are saying it may reach to A4 or A3. Is that in that sense we have written here?
Yeah, it may reach A4 or it may reach A3.
Or A3.
And
Okay.
And A4 it will reach with the probability of whenever you add this, you'll get what? 0.98.
Okay.
And yeah, that time I forgot to consider this part. Yeah, okay. And this will come 0.02. So when you add them, it will come to 1.
Yeah.
Okay. Okay, good. So and then you can keep doing this. Now there are some okay, I'll give you one last example, and that is or maybe I give a question about this. Okay, yeah, okay. So here's another example, maybe a practical example. What is a Markov chain representing tossing of fair coins? Okay. So what is the sample space? Not sample space, it's called the state space, sorry. What is the state space for tossing of coins? What are the states possible? I mean, what are the most natural states you can consider?
Heads or tails? Both.
Heads or tails? Okay, good. Now you need to think of the associated random variable, okay, which is now x1, x2, x3, and so on. Okay. Another thing you need to think about is the probability. So let's say I have two states, which is heads and tails. Let's say my start state is heads. Okay. Now, if my start state is heads, then if I toss a coin fairly, what is the probability that I'll get tails?
1 by 2.
1 by 2 only. Okay. And another probability is I stay at heads. So I have a self loop here. Right. And let's say I have tails. If I then land at tails, okay, first I got, let's say, tails, t equals 1, I get tails. Okay, t equals 1, I get tails. Then what is the probability that I get heads? Again, 1 by 2. Because it's a fair coin and it's an independent toss. And what is the probability that I again get tails? Again, 1 by 2. So it is clear that the Markov chain. So it is clear that this Markov chain represents independent tosses of fair coins, right? Now, what this model is not able to capture is what if the tosses are not independent? What if first I come at heads? Okay. So I start with heads. Then in one step I go to tails. What if I have a scenario where because this first step is tails and my tosses are not independent, which actually does. Oh, okay. Did I stop broadcasting? Hello.
No, you are online.
Oh, I'm online. That's very strange. It says that I'm not broadcasting. No, I mean, are you able to see my screen?
Yes, I'm able to see your list.
Okay, that is. Okay. One moment. It says that I'm not broadcasting. Okay. And even the Gmail tab is closed here. Okay, let me come back here. Okay. Okay, good. So now let's say they were not independent. Okay. Oh, there seems to be. Okay, good. So let's say they were not independent. Let's say if it depends whether the previous toss was a tails or heads or something like that. Okay. If it was not independent, this model is not able to capture that. So this is Markov chain is what is called a memoryless model. It forgets what the previous state was. You just remember the current state and then according to the probability it moves. It does not, the probabilities do not change when you are in a certain state. If you land at the same state, the probability is still same of moving to another state. Okay, and if you've done, let's say, some automata theory kind of courses, okay, automata theoretic courses, then you may relate it with um, finite automatas. But even if you've not seen finite automatas before, but that is completely fine. But the idea of memoryless also appears in automata, and the automata is an example of a memoryless computing machine. Okay, but okay, now that this thing is done, now this is how you represent. Now what is okay? So what is x1? Say so x1 is half. Sorry, x1 is heads with probability half, tails with probability half. Now x2 is what? Heads with probability half, tails with probability half, and so on. Clear, right? Now, one way to actually think about probabilities is think about Markov chains is the following. Okay, I'll demonstrate it with this question. Okay, so the question says the following table shows that the probability of next day's weather is given by the current day's weather is this. Okay, and question says what is the probability that it. Okay, so what is this? This means current day, and this means tomorrow. Okay, so if it is sunny, then the probability that it is sunny again is 0.8, and if it is sunny today, the probability that it is cloudy is 0.15. If it is sunny today, then if it is tomorrow is rainy, the probability of tomorrow being rainy is 0.05. Okay, now what does this remind you of? This is the transition probability table, right? And what are the states? Well, the states are sunny, cloudy, rainy, and so on. Okay, so the first question is very simple. Okay, what is the probability that it rains tomorrow given today is cloudy?
0.2.
Today is cloudy. 0.2. 2. Rains tomorrow. No.
Because
No, the current. These are the current days. These are the next days. What is the probability that it rains tomorrow given that today is cloudy? So today is cloudy.
so that is 0.1.
That's 0.1. Correct. Okay. So what is the probability it rains tomorrow given today is cloudy? Let's see. So today is cloudy, and then tomorrow is rainy. The probability associated is probability that X is today is cloudy, right? Okay. Given that today, which is the start state, is cloudy, what is the probability that tomorrow, that is x1, in one step, okay, it rains? And this table is nothing but this table gives the probability of coming from cloudy to rainy. That's what you're asking, right? P cloudy comma rainy. Probability of moving from cloudy weather to rainy weather in one step, which is one day for us. And this is cloudy to rainy, which is 0.1. Okay, fine. What is another way to see this? What is another way to see this? Well, we make a diagram of this. We make a graph out of this. We have three states: sunny, cloudy, rainy. Okay. Okay, we have three states: sunny, cloudy, rainy. Now, sunny is okay. Sunny to sunny is 0.8, 0.15, 0.05. Okay, and cloudy is 0.3. Cloudy to sunny is 0.3. 0.6 to itself 0.1. Ah, 0, 1. Sorry, this was sunny to rainy 0.05. Okay, and finally from rainy to sunny is 0.5. Okay, and rainy to cloudy is 0.2. And rainy to rainy is 0.3. Clear? Okay, good. Now, this is our setup. Okay. Now you can ask the same question. What is the probability that in one step, okay, if today is cloudy, what is the probability that tomorrow is rainy? Well, now what is your start state? Your start state is today is cloudy. So this is your start state. From cloudy, in one step, what is the probability that I go to rainy? That is 0.1. Right. So answer is 0.1. Simple. Now let's look at the second question. What is the probability that it is cloudy the day after tomorrow, given that today is sunny? So you can use the example that I gave previously. Okay, that time there was no labels or uh, uh, reason, right? But let's say in this case, what is the probability that it is cloudy the day after tomorrow, given that today is sunny? So I'll give you some time to compute it. Okay. So here this answer is this answer was 0.1, and B is probability that today is cloudy. Oh, what is the question? That it is cloudy day after tomorrow, given today is sunny. Cloudy day after tomorrow, given that today it is sunny. Okay, one moment, I need to turn off my low power mode. Because it will shut down. Okay, so try this question once. Okay. Give me a minute. Yeah. Hi. So, did you try?
Yeah. See. So what we have given is today, and then expectation is to evaluate about the day after tomorrow. So irrespective of the tomorrow. So we'll have multiple, just like we have studied in the graph, right? So one is sunny, and then directly 0.15, then again a self loop of cloudy.
Then self loop of cloudy. Okay.
That is one way.
Okay.
And then sunny to rainy, and then
I'll start
rainy
highlighting
to
them. Okay. Just one moment. So one way is cloudy and then to itself. Okay. Good.
yeah. And
Another another way is
another is sunny to rainy and rainy to cloudy.
sunny to
That is
rainy.
0.15
Yeah. Okay. Sunny
multiplied
to
by
rainy, rainy to cloudy. Rainy to itself. Oh wait. No. Today is. Oh yeah. Okay. Rainy to cloudy. Oh. Okay. Just one moment. I need to pick this up. Sorry. Hello. Okay. Okay. Thank you. Okay. Coming. Okay. One moment. Yeah. Very sorry for that. Okay. Continue. Sorry, Kishore. Okay.
and third one is sunny self loop and then sunny to cloudy.
Sunny self loop. Sunny to cloudy. Okay. Okay. So is are all the cases done? So is everyone satisfied with it? Yeah. Okay. Um, yeah, I think it looks good. Okay, let's see. Okay, so first case is okay. Now let's start adding up the probabilities. Okay, so it is probability that um, cloudy day after tomorrow. So in t equals 0, 1, 2. Okay, what is the probability that it is cloudy starting from, okay, or I'll write it, cloudy day after tomorrow is given by probability that at two steps um, t equals 1, t equals 1, sunny to cloudy could be, I move to cloudy first with 0.15 probability and then to cloudy itself 0.6 plus sunny, which is 0.8 to itself, right? Uh, and then I move to cloudy with 0.15 probability plus 0.05 probability of moving to rainy times 0.2 probability of moving to cloudy. So can one of you compute this? 0.15 times 0.6. Let's see. 0.15 times 0.6 plus 0.8 times 0.5 plus 0.05 times 0.2, which is 0.5. I'm getting 0.5. Is that correct? Okay, are you guys following? Goel, Santhya, Shruti. Hello. Hello. I'm audible, right? Oh, okay, okay, great. Um, yeah, so it's coming to 0.5. Please verify that, okay? And yeah, Kishore.
I think it's in the second step, right? It's 0.15, 0.8 into 0.15.
The second step, 0.8 into 0. Oh, yeah, that's correct. So it is
The total calculation is 0.22.
0.23.
22.
22. Okay, okay. So with 0.22 probability, I can, I'm good. Okay. So 0.22 probability in 2 days, okay, it will be cloudy if today is sunny. Now, I hope that is clear. Okay. Goel, you can hear me, right? Goel is strangely awfully quiet today.
Yes, I can hear you. Yeah, but simultaneously I was also within some other thing. But I can hear you and I can understand this. Yeah.
Oh,
Sorry.
okay, okay, great, okay. So now this is the first thing, but now what I want to say is that it gets tiring to compute for several days, right? I mean, if I now ask you for 4 days, for example, C is asking what is the probability that it is cloudy for 4 days from now, given today's sun. Now it becomes very tiresome. Now what you can do is you can make use of the transition probability. Okay, an alternate application of transition probability matrix. Okay, alternate transition probability, application of transition probability matrix. So this is simply the transition probability matrix, right? 0.8 whatever. Let me try to, okay, can I copy it? Oh, great. Right, this is perfect. Oh no, okay, I cropped it. Can I paste it now? No. Okay. Anyway, I'll just write it with my 0.8, 0.15, 0.05. 0.3, 0.6, 0.1. 0.5, 0.2, 0.3. Now here's the fun part, okay? I have this transition probability matrix, okay, which is called P. If I multiply it with my current distribution, then I'll get the next distribution. Okay, now what is a distribution? You might have seen in the lectures, but still, what is a distribution? Distribution, okay, it can be interpreted in two ways, but a simple way of distribution pi of uh, uh, some a, okay, where a is in the sample space, okay. Distribution is nothing but a probability function, okay. A is in the sample space and probability that probability of x equals a. So distribution is nothing but a probability function. So at different for different values there is a different distribution. There's a different probability associated. Okay. For example, we say uniform distribution, right? Uniform distribution means that for every possible value there is equal probability of them happening, and then you have the Gaussian distribution, which says that the probability for the mean is the highest, and so on. Median is the highest, and so on. So that is what a distribution is. The distribution here is nothing but your xi's. If you see, let's go back here and see this. This is a distribution. It is A1 with probability 1 and all other A2, A3, A4 and so on with probability 0. It is X1 is A2 with probability 0.1, A3 with probability 0.9, and for all rest values it is 0. So each of these are actually distributions. So now if you say, what I'm saying is, if you multiply, okay, so this is P. Okay, if you multiply the current distribution with the transition probability matrix, you're going to get the next distribution. Okay. Now, let's see. The question says, what is the probability it rains tomorrow given that today is cloudy? So what is the current distribution? Current distribution x0, okay, is, today is, what is the question? Probability rains tomorrow given today is cloudy. A, today is cloudy. What probability for tomorrow? Probability for rain tomorrow. So what is the distribution today? Today, okay, let's say I do sunny, cloudy, rainy, right? That is the order. Okay, sunny, cloudy, rainy is my state space. Remember that. Today it is sunny with probability. Today is cloudy with probability 1. Today it's definitely cloudy because today is the start state, right? And sunny and rainy with probability 0 each. So now what do? I simply multiply this x0 with my transition table, probability transition table, okay? And which is this 0.8, 0.15 and so on. I'll just copy this. So I'll just copy this and paste it here. Okay, so what is x0? X0 is 0, 1, 0. No? So this is x0 times P. What my claim is? My claim is this is equal to P. This is equal to x1. So this is a distribution of the next day. So let's see. So if I do 0, 1, 0, okay, times this, okay, first of all, what is the dimension of the resulting matrix? This is 1 cross 3. This is 3 cross 3. So we know for matrix multiplication, the rows of the first matrix, the columns of the first matrix and the rows of the second matrix should match. So which is matching, we can do a matrix multiplication, and the dimension of the resulting matrix is the rows of the first matrix times the columns of the third matrix, which is a 1 cross 3 matrix. So it is a single row with 3 columns. It is a single row with 3 columns. Now let us multiply them. Okay, so the first one is 0.8, 0.3, 0. Okay, so first one is I multiply this with this, right? So what do I get? 0.3. Next I multiply this with this. What do I get? 0.6. Next, what do I multiply? I multiply this with this. What do I get? Well, I get 0.1. And this is sunny, cloudy, rainy. So what is my answer? Today is cloudy, which was determined by the first distribution x0 because it was 1 with probability, cloudy with probability 1, right? And this is my x1. Tomorrow's day, I mean t equals 1 in one step, okay? It is sunny with probability 0.3, cloudy with probability 0.6 and rainy with probability 0.1, and this I can extract as my answer. So probability rain in t equals 2, t equals 1 is equal to 0.1. This is my answer. So it is clear that but you can experiment around and you can maybe even prove it. Okay, but it is clear that when you multiply the current distribution with the transition matrix, you get the outcome for the next step, the resulting distribution for the next step. Okay, so that's why I say if I want to find x2 now, okay, if I want to find x2 now, what do I do? But the start state, initial state x2, given that initial state is cloudy. Starting from cloudy, all I need to do now is multiply the x1 to my probability matrix. Now I use this distribution. And similarly, if I wanted to find x3, then I will multiply x2 to probability, and so on. Right? But what is x1? x1? x1 is x0 times probability. So that means that x2, if we substitute x1 there, is x0 times p, which is x0 times p square. Okay. Now what is x3? x3 is x2 times p, where x2 is what? x0 times p square. So, which is equal to x0 times p cube, and so on. If I want the distribution for x4, then I'll do simply x0, the starting probability, times p to the 4. And now you can see that this is actually a more simpler system to do it, to achieve it. Okay, we'll apply it in this question. What is the probability? Okay, let's apply it in the first question first. What is the probability that it is cloudy the day after tomorrow, given that today is sunny? Day after tomorrow means what? I start with t equals 0, which means today. Tomorrow is t equals 1. Day after tomorrow is t equals 2. Given that today is sunny. So, question B, part B is today sunny, probability tomorrow, day after tomorrow, cloudy. How do I do it? Today is sunny, which means the start state, which is x0, equals sunny with probability 1, cloudy with probability 0, rainy with probability 0. Right. Now, what is now what do I want to find? I want to find the probability day after, in 2 days, after 2 days, given that I'm starting from cloudy, is equal to the start configuration, which is x0, times transition probability matrix, which is transition probability matrix square, because it is after 2 days, right? So I just do 1 0 0 times this guy, copy,
x0 is 0 1 0.
Today is sunny, right? So sunny comes first, no? Sunny, cloudy, rainy. What is the question saying? What is the probability that cloudy the day after tomorrow, given today is sunny? So x0 is 1. X0 is 1 0 0, right? Sunny with probability 1, cloudy with 0 probability, and rainy with 0 probability. Okay. Okay. So now I have this. Now, so 3 1 this square. So now what I can do is, first let me compute Actually, I can do a simpler thing, but let me do the more complex thing. Let me compute the square of this first, which is should I? Okay, it may be a bit painful to do the square first, but let us do it anyway. 0.1, 0.5, 0.2, 0.3, multiplied with again the same thing. So if we multiply this, which is actually a bad thing to do, it's better to multiply these two, right? Because it will reduce the number of multiplications. Okay, but later on it may come in handy. Okay, fine, we'll do the easier thing. We'll multiply this first. So this first we already know what the answer is, right? It comes to something like 0.3, 0.6, 0.1. Oh no. Okay, this time it's not 010, it's 100. Okay. Anyway, it's just 0.8 plus 0.8, 0.15, 0.05. Anyway, it's that. Okay. Now let us multiply with the remaining part. 0.8 So here the resulting matrix is what? 1 cross 3 plus 3 cross 3. Resulting matrix is a 1 cross 3 matrix. But it will be a longer calculation. It is 0.8 times 0.8, which is 0.64. It is plus 0.15 times 0.3, which is 0.045. I may be making mistakes here. And 0.5, 0.025, is that right? 0.025. Yeah, you were saying something?
It's 0.64, 0.45, 0.025.
0.45. It's not 0. No, it should be 0.045, right? You're multiplying two very small numbers. So
no, 0.15 multiplied with 0.03. That comes to 0.45.
0.045.
0.045. Right, Shruti. Because you're doing 0.15 times 0.3. If it was times 3, then it will be 0.45. It's 0.3. So one decimal place will be smaller, no?
Okay.
Right? 0.3 times 0.15. 0.3 times 0.15. Yeah, it's 0.05. Kishore. 0.045. Right?
Right.
Right, okay. And let's continue. Next is 0.15 times 0.8. Okay, I'm using my calculator. What was that? Okay, 0.15 times 0.12. 0.12. Good. Okay. Plus 0.6 times 0.15. That will be
0.09.
Okay, 0.09. Now 0.05 times 0.2, which is 0.001. That's what it should be, no?
Yes.
Okay. Now the third value, okay, now it should be 0.8 times 0.05, that is 0.004 it should be.
Yes, sir.
Okay, plus 0.15, okay, this will be 0.015 plus 0. Okay, 0.015. Okay, great. Okay, so but one thing we are doing is we are computing several values simultaneously. That's something you can see. I hope that you are not just computing cloudy, sunny, and so on. Yes, Shruti. You're saying something? 64 plus 0.045 plus 0.025, 0.71, 0.1 plus 0.09,
0.22.
0.22. Oh, that makes sense. Okay, 0.22 and 0.004 plus 0.015 plus
The total matrix, resultant matrix is 0.710, 0.22, and 0.169.
0.169.
Yeah.
Did I make a mistake here? It's both 0.015, 0.015. Is that correct? Okay.
The third,
Okay. Third one.
the summation of 0.004, 0.15, 0.015.
Oh, okay. There I made a mistake.
So
No,
that is third term.
No, this should be 0.015. No, this is correct.
Not that one, sir. Middle one.
Middle one. This no.
Middle. Second column.
Okay. This. Okay. Sorry.
Second column, third one.
Second column, third one. So you mean second column, third one. This shouldn't be 001.
It should be 0.01.
0.01.
Yeah.
Oh, okay, great. Okay. But the answer is 0.22.
22 is correct, sir.
Okay. And the final summation?
0.07. 1 less.
Okay.
It's
Sure.
169. It's 169. Because the summation of 0.004, 0.15, oh sorry, 0.015.
4 plus 0.015 plus 0.034. That's what I'm getting. Is that correct? Okay, 0.2. Okay. 0.034. Is that correct?
Point in third part, first one. 0.8 into 0.05 is, I think, so 0.04, sir.
Okay, one moment. 0.8 into 0.05 is okay, it's okay, 40, so it will be 0.04. Correct. Okay.
So total is 0.07.
Yeah. Another way to do it would be 1 minus this plus this, because clearly before it was not adding up to 1. Now the distribution is adding up to 1. Okay, good. So yeah, now what is the question? We did all this calculation. Today is sunny, probability day after tomorrow is cloudy. That is sunny, cloudy, rainy. So the answer is 0.22, which is same as, note that it's the same as what we got before. Answer is 0.22. The previous was an analysis using the transition table. Sorry, the diagram. Right now, it's simply using matrices. The advantage of using matrices, another advantage is you are computing several values simultaneously. I mean, you may have seen something like this in, say, uh, some AI application, some weight multiplication in, neural networks and so on. It is helpful to use matrices because you can compute several values simultaneously, and that's what you get here. Now, next is, what is the probability that it is cloudy 4 days from now given today is sunny? Well, here I'm not going to compute it because it's going to take time, but this is nothing but t equals 4 given that today is sunny. So start state is sunny. So what is the starting distribution you start with? What is x0?
X0.
Yeah, x0 is
It's cloudy
100.
given today is sunny. 0, 1, 0, 0.
right.
Again, same.
Yeah, good. So it's 100, and the multiplication is x0 times transition matrix to the power 4. That will give you x4. x4 when you are starting at 100. Okay. Now I move on to the next concept, okay, which is this: compute the stationary distribution of Markov chain represented by the chart. Okay. Now, what is meant by the stationary distribution? Of course, this is done in much more detail in the lectures, but simply I'll tell you this. Okay. A stationary distribution is a distribution that does not change on transition. Now, what does this mean? Well, it means that if I have a distribution, say pi is a distribution over the state space over the state space omega, okay, which was for us was sunny, cloudy, rainy. Okay, it is a distribution. If I multiply pi with the transition probability, which means I'm doing one step simulation of the Markov chain given this particular distribution, I get the same distribution. Is that clear? So pi is the distribution over omega. Then if I multiply the transition probability matrix, I get the same distribution again. So it means that no matter how many times given that point on, when I reach this particular stationary distribution, okay, okay, sure.
In that sense, always probability matrix will be identity matrix.
Probability matrix is
when we multiply pi multiplied p, it always results in pi. So that means p is an identity matrix.
No. Why? Because this pi is not a vector, it is a scalar. Oh, sorry, it's a vector, sorry. So, it is true, I agree that one direction is true, that if P is an identity matrix, then what I'll get on this side is also pi. But the other direction is not true, that if what I get is pi, it needs to be that P is an identity matrix. Okay, so what I mean by that is there could be other matrices satisfying this property. Of course, I'm not saying no. Why should that be true? Why should that be true that it is not always the identity matrix? Because I'm saying I don't have to satisfy this for all pi. I'm saying for one particular distribution, my P should be such that if I multiply that particular distribution with P, then I get pi. You get it, right? So if it was identity, yes, of course, I can multiply with any pi for all I, any pi I, I'll get pi I. I'm relaxing the condition. I'm saying, I'm not saying for all pi, I'm saying there exists. There is one specially designed pi for that particular transition matrix, that when I multiply pi with that transition matrix, I'm getting the same pi. You get it, right? So it need not be that pi is a identity matrix.
Is that mean what we can say is there exists a probability distribution matrix which is not identity matrix. When we multiply that matrix with the pi distribution, then we'll get a pi.
Definitely, yeah, right, right. Okay, so let's say there exists a distribution pi over omega such that when I multiply pi with this fixed p, okay, is equal to pi, okay, so for a probability transition matrix p, suppose there exists a distribution so that when I multiply with the matrix I get the same thing, then pi is said to be the stationary distribution for P or for Markov chain represented by P. It represents a Markov chain, and pi is said to be the stationary distribution for that Markov chain. Right. Now, why is stationary distribution important? Okay. Stationary distribution is important is because it characterizes the Markov chain in a sense that if I reach that particular distribution, I can first of all stop running the Markov chain again and again because I know I'm going to get the same probabilities. And another important thing is it is pi is said to do okay no matter what state I begin at. Okay, this is important. No matter what state I begin at, if I multiply it with this particular set of probabilities, then I'm going to get the same set of probabilities. So this means that no matter what state I transition to, I'm over and over getting the same thing, getting the same values, right? So this is this is why stationary distribution is an interesting thing. Okay. Now there are two questions. Okay. First of all, how do we compute the stationary distribution? And the other question is stationary distribution for Markov chain always guaranteed? These are the two questions, right? So can I have a Markov chain where stationary distribution does not exist? Okay. So I'll deal with that first. Okay. So the question says, not question. So here is a lemma, okay, or a fact which says that if Markov chain is finite, it has finite number of states, irreducible, and aperiodic, then stationary distribution always exists. Okay. If Markov chain is finite, irreducible, aperiodic, then stationary distribution always exists. In fact, the stationary distribution is unique, which means it is not possible to get several stationary distributions. There is just one distribution which is stationary, and it is unique to that Markov chain. So it sort of characterizes that Markov chain. Okay. Now, what does it mean? Finite. Okay. Finite means finite number of states. Finite means finite number of states. This is fine. Now, irreducible. What does this mean? This means every state is reachable from every other state in finite steps, infinitely many steps. So there exists a non-zero probability of landing from one state to another. This is what is called irreducible, or sometimes in some books it's also called ergodic. Okay, but irreducible is a better word, I feel personally. And finally, aperiodic. Now, aperiodic, it means that your Markov chain does not have what are called sort of infinite loops. Okay, it means that what is aperiodic? It has a more mathematical definition, but I'll just say that um, it should not be that in every t equals a k steps, okay, where a k is greater than 0, that xt is equal to some state always, xt equals 1. Okay, this is what is meant by aperiodic. For example, tossing coins. Okay, for every even toss, I land at heads, and for every odd number of tosses, I land at tails. So here A is 2. Every 2k steps, I'm landing at the same state. So that is what is meant by aperiodic. Now, if all the states are aperiodic, all states are aperiodic, then Markov chain is aperiodic. Okay. Now, if all the states are aperiodic, then I cannot guarantee a unique stationary distribution. Okay. Now, I hope those things are clear. And now, I'll come back to this. Now, next thing is how to compute stationary distribution. Okay, how to compute stationary distribution? Well, it's as follows. Now I'll come back to the question. Okay, compute the stationary distribution of Markov chain represented by the chart. Now they are asking this. This is the chart, right? Now let me copy this. This is the final question, no, final part. Stationary distribution. Stationary distribution is something that when I multiply with pi, I get pi. Right. Now let's suppose pi is equal to 3 values, right? It's a 1 cross 3 vector. So let's call it pi sunny, pi cloudy, pi rainy. Okay, SCR. Okay, or to make things simple, I'll just call it SCR. Painful to write. Okay, now let's say this is the distribution. So what do I have? I have S C R times this. Right, is equal to what? Pi. Again SCR. And another fact is that S plus C plus R equals 1. So now what do I have? What do I have? I have a system of linear equations on 3 variables. How many unknowns are there? 3 unknowns, and I have 4 equations. I can easily solve them. So let me multiply this. Okay, now okay, this is separate. This is, and also okay, this. Now I multiply them. Okay, now 0.8 S plus 0.3 C plus 0.5 R is equal to S. 0.15s plus 0.6c plus 0.2r equals c. 0.5s no 0.05s plus 0.1 c plus 0.3r equals r. And finally, I also have s plus c plus r equals. So this is 4 equations, 3 unknowns. Okay. Now if I solve this, I'll get the value of SCR, and that will be, now that will satisfy this property, which is nothing but satisfying this property, and therefore the pi that I get will be of this special kind that whenever I multiply with p over and over again, does not matter which state I am in, okay, it will give me the same probability distribution always. Okay, is that clear?
Can you repeat the last statement?
Yeah. So the last statement is okay. I want my stationary distribution will always satisfy this property. Okay. Of course, here I'm assuming that my my Markov chain is aperiodic, finite. Finite, clearly the given Markov chain is finite. There are no infinite states, and I can also figure out that it is what do you say, irreducible, because it looks like everything is reachable from every other state. Now, what I'm saying is, if pi is a stationary distribution, on applying the transition probabilities, okay, on multiplying with the transition probability matrix, I will get the same probability. Now, what I'm doing is I'm assuming the transition probability, I'm assuming the stationary distribution pi to be of the form SCR. Now, firstly, S plus C plus R equals 1, because this should be true for any distribution. Okay, the sum of its probability should always be equal to 1 for any distribution. This is one equation. Now, what I'm doing is I have this, I multiply these two, and then I get these. Right, by equality of matrices, I get these equations. Now I have 4 equations and 3 unknowns. I can easily solve and get those 3 unknowns. What are the 3 unknowns? SCR. And what is SCR? It is the distribution pi. SCR is the distribution pi. Now what does pi do? By construction, my pi satisfies this property that on multiplying with this vector, I'll always get pi again. And because this property is satisfied, it is nothing but the stationary distribution. This is how I compute the stationary distribution. Is that clear? So, yeah, Kishore, is that clear?
Yeah.
Okay, great. So, then I can compute this. So this you can do it as a exercise, okay? And on computing this, the transition probability, the answer should come to, okay, try it. This should be the answer. I'm not 303 0.169 0.448. This should be the answer, okay? Just cross check it, but I'm not guaranteeing this, but try it by yourself offline, because this may take some time, but it's a simple simultaneous equation problem, so it shouldn't be much of an issue. That's what I think. Okay, try it please. But you get it now. This is what is called the stationary distribution, and now that we have this, now next thing we want to tackle is okay, how to compute stationary distribution. That is done. Okay, now we come back to this. Okay, now I want to state something stronger. Okay, firstly, I already stated that Okay, if it is finite, it is irreducible, then the stationary distribution is unique and it always exists. Now I want to say something stronger. What is the stronger thing? If it is finite, irreducible, aperiodic, then definitely I am going to reach the stationary distribution. Okay, definitely I'm going to reach the stationary distribution. For example, this sunny, rainy, cloudy example that had some probabilities associated with it, I am going to, that I go from S to C. So the starting distribution is 1, 0, 0, right? And then I go from S to C with some probability, S to itself with some probability, and S to R with some probability, and so on. Then I move with, and this red is represented by some distribution. And then again I run it for another step. I run it for another step. This, let's say. And I run it for another step, something like this and something like this. Blue is the other, and then I get this. And this is x0. This is x1, x2. And then I continue. It should be that I have an finite value of xi, where xi is equal to the stationary distribution. And what does that mean? For any j greater than I, xj is equal to xi. The distribution does not change only because of that property that this distribution remains the same whenever I apply the probability transition, multiply the probability transition matrix, which is akin to running the Markov chain for one more step. Okay, so here is the statement. Okay, here is a stronger lemma which states the same thing, blah blah blah, finite if my Markov chain is finite, irreducible, and aperiodic. There is a unique stationary distribution. This is what we stated first. Now what I state is that the Markov chain converges to the stationary distribution. What do I mean by convergence? Gets closer and closer after each run. In one step, I get slightly closer to the stationary distribution. Second step, I get slightly more closer, and then closer and closer until I reach the stationary distribution. Okay, and it does not change. Well, the stationary distribution may be very far away. That is true, but I'm fine even if I get some factor close to the stationary distribution, which is still fine. And that is now what I'm going to define next, which is called how long until I reach the stationary distribution. That is a natural question, right? How long does it take to reach stationary distribution? Well, it may be different for different objects, okay? But there is a term for it which is called the mixing time. Which is represented by T mix epsilon. Okay? T mix epsilon. So that is, I'll give you the formal definition. Okay. Now, but of course, now what do I mean by it gets closer and closer to a distribution, right? There should be a method of comparing distributions, how close distributions are. Okay. So for now, I'll just say this much. Mixing time is nothing but it is the minimum amount of time required for the distance between, okay, distance, okay, this TV I'll explain, okay, between the stationary distribution, okay, and this minimum and the initial distribution. Minimum time required, okay, such that the distance between the stationary distribution and the to be at most epsilon. If not the initial distribution, the distribution after time t. So I'll write xt. After t steps, I get a distribution and I compare it with stationary distribution. How close is it? If it is at most epsilon, if it is smaller than epsilon, then I'm epsilon close to mixing time. So what this fact is also what is called epsilon close to stationary distribution. So this is a measure of how much time it requires to reach the stationary distribution, and this is what is called mixing time. Okay. Now the next question is, what is dist TV? Like this measures distance obviously, but there are so many ways to measure distance, right? Like Euclidean distance or some kind of other metric and so on. Now this is what is called the total variation distance. Okay. Dist TV here is what is called the total variation distance. Okay. And so what is that? This is the I do half of, okay, I go across, so let's say I have two distributions, x and y, okay, then what do? I say x equals x okay, probability of x1. Okay, I think there's a much better way to show it, but okay, x okay, yeah, it's a better way to say is so x and y are distributions over omega. Yeah, that makes sense. So x and y, they are just showing probabilities of elements in omega. The elements in omega could be again, rainy, sunny, and so on, or heads, tails, whatever. So the x y is equal to half of, okay, half of summation. Okay, I just need to check this one. Just a moment. Okay. Summation is outside. Summation of a in omega and x of a minus absolute value of x of a minus absolute value of, don't be scared, okay, It means a very simple thing. I'll demonstrate it with an example. Okay, so this is how the distance is calculated. The half is only there to keep the value between 0 and 1. Now, for example, I'll give you an example. Here's an example. Okay, there's an example that is, let's say x is 0 0.2, 0 0.8, and y is 0 0.3, 0 0.7. Okay, and distance between x and y, dtv between x and y is half of absolute value of 0.2 minus 0.3 plus absolute value of 0.8 minus 0.7. So you can see it measures the distance between the distributions, each element, each probability of each element, right? And half times which will be 0.1 plus 0.8, 0.7, which is again 0.1, which is equal to 0.2 by 2, which is equal to 0.2. This is a measure of distance. So this is, again, I will repeat my thing again, what I was saying again. If it is finite, irreducible, aperiodic, first of all, there is a unique stationary distribution. What does stationary distribution mean? After a point, my distribution never changes, okay, on running the Markov chain over and over again. Secondly, the Markov chain will always converge, okay. What does converge means? It will get closer and closer and closer to that particular stationary distribution. Now, if it gets closer and closer and closer to the stationary distribution, there should, in a finite amount of time. Now I ask, how much time does it require to get to the get to the stationary distribution? Now, the idea is there is a term for this which is called mixing time, which is the minimum time that is required to get epsilon close to the stationary distribution. That is, what does epsilon close mean? That means the distance between the stationary distribution, okay, and the distribution on running the Markov chain for t times. What is the distance between the two distributions? That should be smaller or equal to epsilon, the value epsilon. Okay. Now, what is the measure of distance I've used? Dist TV, okay, or DTV, which is called the total variation distance. This is a way to measure distance between two distributions. It could be against uniform distribution or against some Gaussian distribution or whatever, but in this case we are interested only in measuring the distance between stationary distribution and the distribution after time t. Okay, and now what is dist TV? How is it computed? Half of, go over each element in the state space and take a difference of their probabilities and take the absolute value and sum them up and divide by half. And here you have an example of how to do it. So far, so clear? Is it clear? Okay, good, sure. Okay, Sandhya, Shruti, is it fine? Okay. Okay, good. Sandhya, is it fine? Sandhya, is it fine? Okay. Okay, so here's the question. Suppose M is a Markov chain with two states A and B with the following transition probability. Okay, so before this, probably we'll do this question 1. Okay, so try this question. So I give the formula for DTV, right? Okay, so try this question. I'll give you a minute. I don't know why there are two. Okay. This is very annoying. Okay. I'll leave it like this. So it says suppose a coin is biased to say heads with probability 60%, sorry, tails with probability 0.4. What is it? 60. Oh God. I'll just cut it. Okay. This is so annoying. Okay. 60% and tails with 40%. What is the total variation distance compared to an unbiased coin? Okay, Shruti says half of 0.6 minus 0.5 plus 0.4 minus 0.5, which is equal to 0.1. Okay. Okay, good. Kishore, you think something? Okay, let's test it. So, what is the state space? Heads or tails? Okay, and so what is the first distribution? First distribution X is 0.6 heads and 0.6 for heads and 0.1 minus 0.6, which is 0.4 for tails, right? Ah, okay, sorry. Seems I did not give the full question. Okay, this is a full question, sorry. Yeah, 0.4, okay. So this is the biased coin, biased distribution. We are saying what is the distance compared to an unbiased distribution, which is y is unbiased, which means it tells heads with probability half and tails with probability half. Okay. Now let's look at DTV. We just apply the formula, simple, which is half of summation of each of the difference of each probabilities for every element. So for heads we have 0.6 minus 0.5 plus for tails we have 0.4 minus 0.5, which is half times 0.1 plus 0.1, which is equal to 0.1. So this is the total variation distance between an unbiased coin, this distribution versus an unbiased. So you can see that 0.1 is very small compared to 1, say it's just 10%. So it says that the difference between these two is 10%. If it was highly biased, say 0.1 for heads and 0.9 for tails, that is highly biased. If you do a comparison, then of course this value will be higher. So it tells you how biased the distribution is. So it's not just about heads and tails. You can compare it to any uniform distribution, say how far is it from a uniform distribution, how far is it from a Gaussian distribution, and so on, and say you can tell things about how biased your data is. Okay, this is an application. Another application is of course using for mixing. Kishore, is it fine? Okay. So now quickly let's do this question and probably then we can call it a day. Okay. Okay, we just have 8 minutes, but I'll just quickly demonstrate this question. Okay. Suppose M is a Markov chain with 2 states A and B with the following transition probability matrix 0.7, 0.3, 0.4, 0.6. Okay. So far so good. Compute the mixing time T mix where epsilon is equal to 0.05. Okay. Now, yeah. Question is, before just now the example we were looking at was with respect to a uniform distribution or unbiased coin, right? If we are talking about mixing time, we are saying the time it takes to get epsilon close to the stationary distribution. So if I have such a question where I'm talking about mixing time, I need to compute the stationary distribution. So step 1, compute stationary distribution. Okay, now how do I compute stationary distribution? Like before, I'll just use a system of linear equations. No? So I have 0.7, 0.3, 0.4, 0.6. I multiply this, so this is my P, this is the transition matrix. So what I need is, I want pi times P equals pi, which is nothing but pi 1, pi 2, okay, pi 1, pi 2 times 0.7, 0.3, 0.4, 0.6 equals pi 1, pi 2. Okay. Now pi 0.7 pi 1 plus 0.4 pi 2 equals pi 1, and 0.3 pi 1 plus 0.6 pi 2 equals pi 2, and finally I have the third equation, which is pi 1 plus pi 2 is equal to 1. This is true for any distribution. Okay, I have 3 equations on 2 unknowns. Okay, now this becomes, I bring pi 1 this side, so this becomes minus 0.3 pi 1 plus 0.4 pi 2 equals 0, and I bring pi 2 that side, it becomes 0.4, okay, it becomes 0.3 pi 1 plus, I bring pi 2 this side, it becomes 0.2, oh no, 0.4 pi 2, right? So I add this up and this will get cancelled, and I get what? 0.8 pi 2 equals 0. Oh no, there's something wrong here. Pi 1, when it moves there, it becomes minus 0.
I think so. Second one minus 0.4 pi 2.
Minus Yeah, okay, good, yeah. But okay, now still there's a problem. Both of them will get cancelled out. Okay, so these are not linearly independent. Okay, so we cannot do this. These are not linearly independent, right? Because both of them can be obtained from each other. But that's okay. I have this third equation which says pi 1 equals pi 2 minus 1. So I'll substitute pi 1 equals 1 minus pi 2, right? And substitute pi 1, so it will become, let's call this 1, let's call this 2, let's call this 3. And using 3 in 1, I have um, 0.3 times 1 minus pi 2 minus 0.4 pi 2 equals 0. So I get, this is hairy, 0.3 minus 0.3 pi 2 minus 0.4 pi 2, 0. So this is, which implies pi 2 equals something like 0.3 by 0.7, which is equal to 3 by 7. Correct?
Yes.
Yeah. Okay, good. And so after this, okay, let me shift this here. This implies uh, that I substitute, okay, this implies pi 1 is nothing but 1 minus 3 by 7, yeah, which is equal to 4 by 7. Good. Okay. Yeah. So stationary distribution equals 4 by 7, 3 by 7. Okay, good. So step 1 is done. Now step 2, I need to run the Markov chain over and over again. Okay. Go across t equals 0, not 0, we already know. And go across t equals 1, 2, 3, and so on. Okay. And find distance, total variation distance between stationary distance. Let me call the stationary distribution pi only. Okay. Distribution between pi comma x comma t, xt. The distribution at that point. And if it is less than epsilon, I'm already done. What is epsilon given to us? 0.05. Okay. And okay, let's do it for one value. Okay, then probably we can stop. So first t equals 1. Okay, initial state, let's assume there are only two variables. Let's assume I'm 1, 0. Okay. Let's say x0. Suppose x0 equals 1, 0. Okay. And now what do? I t equals 1. What do I have? I have x0 times p equals 1, 0 times this table 0.7, 0.3, 0.4, 0.6. Okay. And this is x1. So x1 is equal to 0.7, 0.3. Okay. Now that is obvious. Now I compute the distance between pi and x1 and check if it is less than epsilon. Okay. Now this is the distance between what was pi? 4 by 7, 3 by 7. Maybe it's better to convert them into decimal form. 4 by 7 is 0.571. 3 by 7 is
0.428.
0.428. Good. 0.428 and 0.7, 0.3. Now compare the distance, which is half of 0.571 minus 0.7 plus absolute value 0.428 plus minus 0.3. Okay, again it's a slightly hairy calculation, which will be half of something like 0.57 0.7 minus 0.57
0.129.
0.129, okay, plus 0.128, right? Which will be 0.257 divided by 2 which will be 0.128 point something, which will be around 129. Okay, this is clear, no? Okay, and this is the distance, but 0.129 is not less than equal to epsilon, which is given as 0.05. So I continue this process now. I do t equals 2. So x2 will be x1 times p, or I can do x0 times p square, and this will give me another set of equations. Sorry, not set of equations. It will give me another set of values, which is again slightly painful calculation, which is 0.7, 0.3 times 0.7, 0.3, 0.4, 0.6. And okay, the rest I'll leave it up to you to do the calculations. Okay, now the answer should come to 0.039 if I'm not mistaken, and 0.039 is less than equal to epsilon. What is epsilon? 0.05. So it is less than 0.05. So your answer will be t equals 2. This is the minimum time in which it reaches the stationary distribution. It does not reach the stationary distribution. It reaches very close, epsilon close to the stationary distribution. So t equals 2 will be your answer in this case. Okay, and so that will be your mixing time. Now, yeah, sure.
Let's suppose at T2 we got the answer as close to epsilon. So even when we further extend the step for T3, then what is the value for that? Is it
Oh, you're going to get a smaller value.
Yeah, it decreases, right?
It will decrease. It will definitely decrease. It will converge because this is a this is a finite aperiodic, and what is the third point?
Irreducible.
Irreducible. It is finite, aperiodic, irreducible. It will definitely converge. It will get closer and closer to t, but the t value may be very high, where it will actually reach the stationary distribution, right? So we are fine until we reach some epsilon value. I mean, for practical applications, say.
Okay.
Now, question is, but this is a very experimental approach. No, we can't afford to do this for every time. I mean, this is a very brute force approach. We go 2 t equals 1, t equals 2, and so on, t equals 3, and so on. So therefore, you have something called the coupling lemma, which I did not get to cover this time. Okay, but please look into it. Okay, coupling lemma. Okay, which helps you to bound the mixing time by bounding what is called the by bounding the distance between the total variation distance. You are actually able to perform some analysis. For example, random walks on graphs. If you are doing random walks on graphs, so what is the probability that you reach a particular vertex? For example, I think in one of your assignment questions there is talk about, oh, but this does not require coupling lemma. Okay, this does not require coupling lemma. But there's a talk about random walks on a path of length 10. So, but analyzing the probability for each particular node could require coupling lemma. But just go through the lectures once, you'll be able to solve it. Okay, this does not require it directly. But anyway, coupling lemma tells is very useful, because what you are doing is you are sort of running two Markov chains together side by side, and you are waiting for them to reach the same distribution. Okay, and then once they reach the same distribution, they'll act the same. If they reach the same state and the same distribution, they'll act the same therefore onwards. And I'll fix the second distribution to be, say, the stationary distribution, and that time it reaches to actually reach the same time, same state, is exactly equal to the mixing time. And that is another way to compute the mixing time. And but look into this. I did not get time to cover the coupling lemma, but I wanted to cover the fundamentals of Markov chains, which I hope it is clear to every one of you, each one of you. Okay. Okay, fine then. I think that's all. Just let me know if you have any further questions. Yeah, and yeah, this value will come. Yeah, Kishore, this value will come closer and closer to the stationary distribution. And for example, one lecture is based on card shuffling. Okay, that is interesting. And by the way, if the refer to this Mitson marker book, and this is anyway the reference text for this section for the course anyway. But refer to this if you have any doubts, or you can even mail me. I gave you my email last time, right? And okay, fine. If there are no more questions, we can stop.
Yep. Thank you very much.
Okay, thank you, Kishore.
Yeah.
Okay. Okay, Shruti, Santya, any questions? Else we can stop this.
Nothing, sir. Clear. Thank you.
Okay, great. Okay, thank you, Shruti. Bye bye. Hi, Santya, is there any more questions? Okay then, I'm ending the meeting. Okay, bye.